Swayam Prabha. Digital India. Educated India.
So, if that is the case, what is there in the typical router inside? How do you implement these lookup operations and other things like quality of service, policing, and other things that I was talking about? So, as usual, the routers also had a humble beginning where the things were implemented as a software solution. You write the code and program to do this lookup operation. Basically, this is a string matching and searching operation. And as days passed by and the network speed typically on increasing, the software solution didn't probably won't be able to scale up, or it didn't scale up. So we turned into hardware, and there are several hardware mechanisms that came into our techniques that came into picture. So one is something called as the ASIC. ASIC stands for application specific integrated circuit, meaning that I design a circuit or the hardware specifically to do the lookup operation. So it does only that one, nothing else. And such very customized hardware if you build, then you can scale up the operations. So that will bring, hardware is anyway comparatively compared to the software, it is faster. And on top of that, if you build very custom hardware, not the generic hardware like the one we have in our typical computers, this is only meant for doing that routing and forwarding decisions. So you will bring the scale up the operation. And people also talked about FPGA based implementations. So FPGA is another kind of the hardware technology that in use. And the third one is something called as the TCAM. TCAM stands for Ternary Content Addressable Memory. So there is a difference between the CAM and the TCAM and the typical RAM that we have. So let's quickly understand what is this. The RAM that we have in our computer is called random access memory. So what we typically is, there is an address to every location. Let's say 101 is this location and 102 is this location and so forth. When we want to access something from this memory, we give typically the CPU gives the address. So can you go to this location 101 and get the content? That might be the probably, if like let's say I have 10 here. So 10 will be brought to a register inside this CPU. Every time I want to make this access some content from the memory, I keep giving reference of the address. So go to this address, find this, go to this, what is there, you get me that, go to this location and write this content. So from the CPU register to content would be transferred to the corresponding memory location. But unlike this, what CAM does is, so I'm not going to tell or address you by giving the address, but what I give you is, I want this content. So can you search this content whether in one of your location or more on location? If this content I am looking for 10, and can you find out and quickly tell me whether 10 is there inside your memory, be it anywhere. So whether it is in the first location, second location, third location, or last location, we don't care. As long as it is there, so we are fine. So we just want to find out whether this is there or not there, and if it is there, where it is there, which location it is. That is the option. And the CAM, the content addressable memory, can precisely do this operation. So you give me the content, I am going to search inside my memory locations whether that content is available or not. So if it is available, I am going to tell you this is available and where it is available. If not available, then I will tell you this is not available. So think of this case. I have got an IP address and I want to do the lookup operation, and I can tell this using this memory, I can tell that router, so can you quickly find out, I have got a packet with this so and so IP address, whether this IP address or for this IP address where you have a routing entry inside this, if yes, what is this location, and then what is the port number on which I need to send this. So that is the kind of operation I'm looking at. So CAM perfectly fit this case, but what TCAM says is, typically we talked about the routing entries being in the prefix format. The entries are not in the exactly in the binary format of 10 or something like this, but there are also entries like stars. So 1011 to 1111 star or something like that. I might have 110001 star, and TCAM allows you to do the search operation or the lookup operation using such kind of the prefixes. So I can have every bit can be either 1 or 0, but it can also be a star. I can give a third component, which is the star also as an entry. So I am looking for 1100 star. Can you find out? So it can quickly go and find out, okay, 1100 star is here. So what is its next on which port number I need to forward this? It can quickly come back and tell you, so that you can make the forwarding decision. So such a memory, it is content addressable, but it is not binary content addressable, but it is can also take the stars into account. So it can search keeping the stars or the prefixes, using the prefix directly, using prefixes it can search. That is what in our context it means. So such TCAM memory is also available with the routers nowadays. Using that you can actually bring scale up of operations to the routers, typically to the border routers and the core routers. So that is what the router contains. So if you look at in little more detail what exactly router do contains, as I said, the typical operations of the router is divided into two parts. One is the control plane operation, and the second one is the data plane operation. That is also called as the forwarding plane operation. So in the control plane operation, you have got the routing table. This routing table is being updated. So I got a memory and CPU, and typically every router keep exchanging the information, the routing updates to its peer. So R1 sends its routing table to R2, and R2 sends to R3, and R3 sends to R1, R1 sends to R3, and they keep exchanging this information, using which, so that will tell you whether they have connectivity to this route, this prefix, that prefix. Based on that, they keep updating the routing table. So that is what is happening in this portion of the router component. And we can use typical software algorithms, the normal CPU that you find in your computers and all that. So this is perfectly fine there. But on the second hand, this forwarding decision, as I said, need to be in real time. So I need to have something more. So the things in the forwarding plane are, so one is we have something called as the line cards. These line cards are typically from the cable that you connect to that router. In addition to that, there are some more components. We will see what is there inside that line card in little more detail. But there are a bunch of line cards where the cables come and terminate, and maybe let's say an Ethernet cable or an optical fiber cable terminates, the interface where that cable terminates, and then in addition to that there are some more things. And then second component that you have is something called as the switch fabric, which tell you if I receive a packet on this line card, and I make taking the reference to the routing table that is loaded into this forwarding plane operation. I decide I need to go to this exit line and then forward this packet. The packet comes here and then go to this interface and then exit the router. So the switch fabric allows you to connect from one interface to the another interface, from an incoming interface to the outgoing interface. It establishes a link. If I want to go to the line card number 10, how do I go there? From the input line card number 1. And if I want to go to input line card number 3 and go to the output line card number 4, how do I actually go there? So such interconnection is actually given by this fabric. So the typical operations that are done inside between the packet arrival of an interface card and the time the exit happens, there are a couple of things. One is every hop you need to do the TTL, you decrement the TTL value, you reduce by 1. So that is one thing. And if you reduce the TTL value, then you need to recompute the checksum value. At each hop of the router, you need to recompute the checksum value. So that is done typically at the input line card here. And once you decrement the TTL value, recompute the checksum, you extract the bits corresponding to destination IP address, do the lookup operation, and then quickly decide, okay, I need to go to output to port number 4, and this is the corresponding line card I want to use, and then you push the packet to that particular port number. And at the output layer, when the packet actually comes to this line card, you need to do something more. What is that? Add the link layer header. So meaning, so on an input link, you have a link layer header added that is stripped off at the input line card, and from this route onwards to the next hop, you can add a different altogether a different link layer header. So we think of this case. The first hop, I am a wireless user, maybe using Wi-Fi or a critical GSM network, and I am in a packet, that's a wireless hop. I have a different link layer protocol from this hop, my computer, to the nearest router, and then from there onwards to the next hop, you are exiting, you are entering the core of the network, you might have a different link layer protocol that is working. So typically link layer protocols do the mean for one hop operation. So I have one link layer protocol and typically the corresponding link layer header and the first hop, and I have a different connectivity in the second hop and a different link layer header in the end hop. So what is the next hop link, the link between the corresponding router and the next hop, and depending on that I am going to add the corresponding link layer header, and you send the packet on that particular link. So this is typically what happens in the forwarding plane or the FIB operation. Here is the IP version 4 header. So this is the thing I was referring to. So you have got time to leave value. This is typically we also call as hop count. If it is set to 10, when a packet arrives at a router, particularly the edge router, you make it as 9 and then send it to the next hop. Here is where the line card corresponding to this output link is where the MAC header or the link layer header corresponding to the next hop is actually added. And since the TTL value has changed, the header checksum is calculated on the entire header from here to including the header. So the checksum value will also change. You need to keep updating that also at every hop. Okay, so now the next question that we want to ask is, how do we actually build the router? There is a control plane operation and there is a forwarding plane operation, or the data plane operation we want to call, and these are two different things. So is it that routing table I take and keep it in one place, and then every time I receive a packet on any port I go to that routing table and then do the forwarding decisions? Or there are multiple number of the instances of the routing table itself, and then I can make an independent decision. So if I am a line card, if I receive a packet, then I can quickly consult if I have a local copy and then do the forwarding decision quickly. So depending upon whether a centralized repository of the routing table is kept inside a particular router or there are multiple instances, we categorize such routers architectures as either centralized or distributed. So in the centralized routing infrastructure, what we have is some instances, not necessarily one. Here in this diagram there are 3 copies of the routing table. So there are 3 instances which are going to do the lookup operation, and you have got some number of the interfaces. So you receive a packet here, and you access one of the available forwarding engine at this time, whichever is free, you access that, consult that routing table and do the lookup operation, decide where to send the packet, and then through this fabric you actually route the packet and send it. So if you use such an architecture, then it is called as a centralized architecture. And then along with the switch fabric is connecting the two different interfaces. You got something called the route controller and also management controller. Route controller is meant for constructing that routing table and to deal with the routing algorithms in the control plane operation. And the management controller is meant for manage the configuration of the router. If you want to change the metric, so for example, so typically routing algorithms do use the hop count and other things as the metric. So if I want to update that metric or change the routing algorithm, so I need to configure that router. The interface between the user and that particular router is exposed to this something called as the management controller. So I'll summarize again. Routing controller is the to deal with the routing algorithms. Management control is to do with the configuration of the router. Switch fabric interconnects the different interfaces. The forwarding engine typically do the lookup operation and tell on which output interface this particular packet need to be forwarded. So in the distributed architecture, what we have is, we still have the route controller, we still have the management controller, we still have the switch fabric, but on every interface we have a loaded forwarding engine. So there is a routing table sitting here with a processor, and it has got everything, so it can do the lookup operation independently. In the previous case, there were only handful number of the instances, and everyone was sharing that those handful number of the instances routing table, and then doing the forwarding decisions. But unlike that, here I have an independent routing table sitting in each of the interface, and they are being consulted every time a packet is received on that interface. So you can think that by replicating these instances, I am going to actually, earlier if I, let's say that I have 100 interfaces and then only 10 forwarding engines. So these 100 interfaces need to share only those 10 forwarding engines. But here if you have distribution, since every interface has got a routing table, so I can bring scale up operations. So I don't have to wait for that forwarding engine to become free to do the lookup operations. So typically nowadays, whatever the routers that you see will follow this architecture of the distributed structure, where every interface card has got the interface has got the an instance of the routing table loaded along with the necessary network processor to do the lookup operations. So the typical line card that I was talking about will look something like this. Switch fabric is here, the router controller and the management controllers are here. One line card will have these many number of the elements. So it has got something called a transponder or transceiver. So this is an electrical or optical device which actually are component which actually receive the signal from on a link, and then it knows how to interpret that. So for example, if you have an optical fiber cable, the data is transmitted in the form of the light. There is a signal that is going inside that fiber optic cable. You need to interpret that. Okay, this is when 0 is coming, this is when 1 is coming, and a sequence of zeros and 1 is coming. And the job of this receiver or transponder is to understand the incoming signal and then decide whether this is a 0 bit or 1 bit. Bits are coming serially inside that link. And if you are a sender, then you either send a 0 or 1 depending upon the what is the content or of the packet. So you also have something called as the framer. This is where the layer 2, the link layer operation is coming. That is also typically implemented as part of the client card. So if you receive a packet, you need to understand the header structure of the link layer and then appropriately interpret where how big this link layer header is and where is the next layer IP header is starting and from which offset I need to pick up the bits so that I look at the destination IP address and make the decisions and so forth. So to understand that, you have got a framer. On the other hand, if you are a sender, you are forwarding a packet, you need to add that corresponding link layer header. That is done by this framer. And there is a processor that is sitting, that we call it as the network processor, which does this lookup operation. Because you want to do the lookup operation, there is some computation involved. You are typically searching for something. So that is done by this network processor, and it has got an associated memory. And you also have something called topic manager. The example that I was talking about, along with the forwarding decisions, routers also need to do the bookkeeping operations, like who is sending at the maximum rate, who is sending at the reduced rate, whose traffic I need to forward, whose traffic I need to block. So all these operations are controlled and done by these traffic managers. These are all the typical components that you see on the on a typical line card, including the processor and that is the network processor, framer, and the traffic manager. So that is all about the routing architecture and the components. So these all put together will bring the scale of the operation that we are looking at. So with that background in mind, so routers need to do the lookup operation and some other kind of the bookkeeping work they need to do. And these routers need to do these operations at a massive scale with millions of packets per second. And if I want to design such a router or a switch, what are the typical design goals which a router such a design need to satisfy? So there are a bunch of them. Let's take a look at so one way to evaluate the performance of the router is how many number of the packets this router is able to forward in real time. So packet per second might be one metric with which we can evaluate, or alternatively, if I am the designer, I need to aim for maximum number of the packet per second processing capability. So the more such capability you have, the better it is. So I can do the operation quite quickly, which is required in the backbone and the border routers. And the second thing that you want to aim for or you would like to have in the router is modular upgradation, meaning that we know that things are going to be added, more number of the users are going to be connected, more number of the prefixes are going to be added. So the size of the routing table is increasing, the number of the people are increasing, number of the hosts are increasing. So if I am the network service provider, how do I design my router? So one thing is 10 years down the line, I anticipate that my routing table entries or size of the routing table is going to be size X. So to looking at that 10 years down the line, I am going to build an hardware or a router which is capable of handling the traffic and the scale of operations required 10 years down the line, and that will require cost. So 10 years down the line, what is going to happen? Now only I need to do the capital investment. So I need to bring a router which is capable. So on the other hand, if you have a modular design, currently my traffic is looking like, let's say I am receiving 1 Gbps traffic on my router. I am going to build a router which is capable of handling 1 Gbps, and 2 years down the line this might go up to 2 Gbps. So I am going to add new hardware, new component to the existing router which can handle 2 Gbps of the capacity, and 10 years down the line if I am aiming for 10 Gbps, so I keep adding every year. I am going to add some component to the existing router, and I extend the capacity, processing capacity, lookup operations, everything that I want to do with the router by dynamically or adding the components not in one go but in batch wise. So that will going to help me. I don't have to do the buy the hardware right now itself by looking at the traffic growth for the next 10 years. So that's actually anyway, if I buy the hardware for looking at the traffic growth at the next 10 years, that's going to be underutilized, and you also end up putting a lot of money on that one. So by doing the scalable modular upgradation capability into router, I am going to actually help. I can bring the components as and when, and then keep on increasing the capacity. I am going to add line cards to that router, new line cards as and when new people join, new connectivity going to be there. And I can also add new CPU, new memory, whatever I want. Everything is going to be modular. And the third thing that I really look at in the router is bandwidth density, meaning how many number of the bits that I can handle parallelly in one go. Bits in the sense packets is one terminology. Packets are in turn made up of the bits. The more number of the bits processing capability that I have in my router, that's the better it is. The size is compact, but in the same size I am going to handle more number of the bandwidth, maximum bandwidth. That's better for the router. And in addition to forwarding or lookup operation is the primary job of the router, that's what I said. But in addition to that, the routers also need to do a lot of other things like the policing or quality of service and all that. The more number of such features the router is able to handle on the existing capacity, the better it is. So that is called the service delivery features. So anything other than the lookup operation, whatever you want to do with that router, if your router is supporting that, then it better it is. And then these routers, think of the situation. I am talking about a router connecting the internet service provider networks of several nations. Maybe one link from the India and another link from the USA are coming and terminating at a point, and the router which actually interconnects these two links need to be highly available, meaning that 24/7 365 days it has to run. The moment these routers are down even for a minute, then it will disconnect the two internet service providers for that much time. So I need to design these routers for very high availability in a fault tolerant fashion, so that I can do the operation. I can guarantee that this router is going to function 24/7 365 days. And in order to do that, the routers, typical routers that are available in the market are having a capability something called as hot swappable. Hot swappable is something like this. I don't have to shut down the router to do an upgradation. Typically, let's say if I have a computer and I want to insert a new RAM slot on my motherboard, how do you do that? You shut down the computer, then you open the motherboard, and then on a slot you fix that RAM, and then you start the system and it start functioning, it start working. But that I cannot afford to do in a typical backbone or the border routers on the scale of the operation. So I don't want to put that router. Even the rebooting is also not possible. So in that case, without shutting down the router itself, I can bring the new hardware, plug in there, and it will start working. So that is the kind of the features that I am looking at the very high availability. And then of course the routers, they do use routing tables and making they do have the memory and the CPU to do the processing, and these operations need to be secure, meaning that a false router entry should not come there, somebody should not get hold of are able to manipulate that routing table, influence your routing decision. That should not happen. So these are some of the design goals. These are some of the objectives with which a router design should start with. Now the question is, how do we actually achieve this in practice. If I want to do a quick route lookup, what kind of the data structure that we use to do the route lookup, and what kind of the hardware do we use to do the route lookup. If I want to do the quality of service, how do we actually do, how do we implement that in the software, in the hardware, and what kind of algorithms are being used. That's is the content for the subsequent lectures for this model. We will see some of those examples on the subsequent lectures. So I'll stop it here for this lecture. Thank you.